Okay, thank you, Renee. Thank you, Jerry, for setting up this fantastic seminar series that we've all been enjoying. It's a pleasure to be able to contribute from the UK, where it's about 5 p.m. now. So the title of my talk today is Multimodal Microfocus XAS to Understand and Remediate DU Munitions Contamination. And this is a PhD project of Daniel Crean that was done in collaboration with Swiss Life Source a few years ago. It finished now. So the talk is split into two parts and is based around using multimodal microfocus X-ray spectroscopy to characterize depleted uranium particles for munitions testing. The first part applies these techniques to understand the environmental behavior of DU particulates. And in the second part, we apply these techniques to design more effective remediation measures for DU contamination. So DU munitions are used mainly by the US and the UK, with a long period of testing from the 1960s onwards. I'll just fire up my laser pointer here. From the 1960s onwards, they were used in both Gulf Wars and in the conflicts in Kosovo and Bosnia. And they're used as armor-piercing rounds to destroy enemy tanks. As the penetrator, which you can see here, just coming out of its sabot, as the penetrator strikes the target, the surface temperature increases rapidly, leading to pyrophoric oxidation of the uranium. And this keeps the tip of the penetrator sharp. And it's this property combined with the high density and hardness that makes uranium the material of choice for this application. However, pyrophoric oxidation of the penetrator produces uranium oxide particulates, and the conversion of penetrator to particulates is typically 15 to 35% of the initial mass, and maybe up to 75% of the initial mass. So the potential long-term health risk is from resuspension and inhalation of these particles, which have a small characteristic size. And there may be a requirement to remediate at some sites with high particulate and high contamination levels, such as at firing ranges. So as I said, the work that I'll talk about today was undertaken by Daniel Crean in his PhD using the Swiss light source with the support of UKRI, EPSRC, and the Actin I3 program. And it's published in 2 articles, and you're welcome to consult these if you want to find out more. So this slide explains the source of the particles used in this study. One of the main uncertainties with DU particles in the environment is their long-term behavior. Wet oxic surface environments, we have a lot of wet oxic surface environments in the UK, would be expected to promote corrosion of uranium oxide particles, which will affect the risk posed by the DU residues. So the Ministry of Defence Eskmeals firing range, which is on the northwest coast of England, provides a laboratory to study such environmental behaviour. It's one of the oldest DU munitions testing sites and is heavily contaminated due to long-term testing starting in the 1960s up to 1995. And we collected particles from 2 sites with different contamination pathways. So site A here is a kind of typical scenario. So the particles are scattered from the DU penetrator impact at the target area here, and they settle in near surface soils after impact. The soils here, from total chemical digest and analysis, have a uranium concentration about 1 order of magnitude above background. And site B is a little bit different. So that's behind the target area here in this kind of forest area. Target site B has heavily contaminated uranium soil with uranium concentration about 2 orders of magnitude above background. And this is due to the fact that in this area, the timbers which support the armor target here have been disposed, and these are heavily contaminated. And the soil here has a high organic matter content as a consequence of the co-disposal of the uranium residues with the timbers. So those are our 2 sites from which we've recovered particles. So this slide summarizes the X-ray techniques used in this study. at the microfocus beamline at Swiss light source to spatially resolve information about element composition, phase composition, and uranium speciation, primarily oxidation state. So the micro XAS beamline is a hard X-ray beamline on an undulator source with a flux of about 10 to the 12 photons per second at 400 milliamp ring current. The size of the X-ray beam is governed and by focusing using a set of Kirkpatrick Bayes mirrors to give a spot size here at the sample of about 2 by 5 microns. On this slide, the beam comes from left to right, and the sample is translated here on this stage and moved in the beam. The signal of interest is monitored at each step or pixel to create two-dimensional maps. The intensity of characteristic X-ray emission of the elements of interest are monitored for elemental mapping, so that gives us XRF maps. And these are then used to identify points of interest for further investigation. So they can be interrogated by Zane's step scanning in the traditional method with fluorescence detection, or we can do X-ray diffraction in transmission mode using a Pilatus detector. We also make phase composition maps, as you see here from the X-ray diffraction data, where basically we window a Bragg peak of interest, and then we highlight the corresponding pixels where that Bragg reflection is present in the map, and that allows us to construct maps to show where different crystallographic phases are present in the sample. And we also do what we call oxidation state or chemical speciation mapping, which I'll come on to talk about a little bit later in terms of the methodology. So that's the setup that we're using at Swiss Light Source. So on this slide, I'm showing some data, some typical depleted uranium particles in the near surface soils at Site A observed by SEM, where they appear as bright contrast. So a range of particle types was observed, including characteristic spherical features, as you see here, which have been linked to the melting of metallic uranium under impact conditions, and essentially the surface area is minimized. So many depleted uranium particles are found to be clustered together, suggesting adhesion to and agglomeration with the soil particles and other impact material. The morphology of the particles in these soil samples is consistent with other studies of DU impact material, including controlled firing tests and particles recovered from conflict zones in the Balkans and the Gulf Wars, although the environmental conditions here are clearly very different from those locations. So that's what the DU particulates look like. This slide shows some XRF maps, as you see here, microfocus X-ray diffraction data and Zane's data from representative DU particles recovered from near surface soils at Site A. The XRD data show uranium oxides, primarily U307 and minor U308, which are expected phases produced by pyrophoric oxidation of metallic depleted uranium penetrators. Their presence suggests that these particles do not have a strong interaction with the environment and they stay unaltered in the surface soils. This is confirmed by XRF mapping, which shows characteristic spherical distributions of uranium, also observed by SEM and shown on the previous slide. And the uranium L3 edge Zane's data are consistent with the XRD data. The edge positions and post-edge features shown by in the uranium L3 Zanes of these particles are similar to the UO2 reference for uranium-4 and as expected for a majority U307 phase with a fluorite-related structure. So using XRD, we observed two different uranium oxide phases, U307 and U308. So we used phase or speciation mapping to resolve their spatial distribution. So the oxidation of uranium dioxide UO2 can proceed via U307 to U308. And so the distribution of these two oxide phases might give an indication of any potential weathering or alteration process. What we find though is that the phase distribution reveals distinct domains of U307, so highlighted here in red, and U308, which likely correspond to variations in formation conditions rather than an oxidation mechanism, because the distribution is distinctly bimodal, as you can see. So that's our diffraction mapping there. We also did some oxidation state or chemical state mapping, which reveals domains of two different uranium oxidation states corresponding well to the two oxides I mentioned. So you see we have this region here with an average oxidation state of 5.3, and that ties up well with U308. And then here we have an example of an oxidation state averaging at 4.6, which corresponds well with what you would expect for U409. So that all ties up very nicely. I thought what I'd do in this talk then is to explain a little bit about how we go about the methodology of chemical state mapping, because it perhaps might not be too familiar to some of the PhD students on the seminar. So chemical state mapping can be used to identify areas of different speciation. And the key advantage to this is it's rapid and you get a coverage over a large area, and that can then help you really focus your data acquisition strategy for Zane's data acquisition by step scanning and X-ray diffraction. But it's advisable to cross-check your results with XAS or XRD at a point of interest, because there are many kind of different things that can, or different factors that can control the normalized absorption at any one pixel, as I'll come on to. So this reference here gives you a good kind of summary and introduction to this technique. Okay, so the method then, basically what we do is we use the contrast in normalized absorption at specific energies to infer oxidation state, speciation, or coordination changes in the material of interest, i.e. the chemical state in general. So we selected 3 energies for our study in mapping. So the first was at 17,168 electron volts. And this gives us contrast here in the oxidation state in the leading absorption edge between uranium-4 oxide and uranium-6 oxide, as you see here. The second energy we chose was at 17,185 electron volts, so that's post edge, and that gives us nice chemical contrast for this uranyl resonance in the post edge region. And then finally, we collect a map here at 17,500 EV, so way off the absorption edge, in order to be able to normalize our measured absorption. So then it's very simple. All you do is you collect a map at each characteristic energy, you measure I0 and IF in the normal way, and that gives you then the absorption. But the thing to bear in mind is that the measured absorption in these maps is dominated basically by concentration gradients. And so that's why you have to normalize to this third energy here, way off the absorption edge. So if we divide these two maps through by the third, we get a set of maps that look like this, where now the normalized absorption scale begins to bring out oxidation state contrast in this case. So here we've got a region which is more absorbing at the lower energy map, and that would be consistent with a more reduced uranium species, and out here a region which is less absorbing and therefore is probably more oxidized. So the final step then is basically then to calibrate the normalized absorption scale using a set of reference compounds of known oxidation state, and then when you do that, the product is a uranium oxidation state map that looks like this. But clearly the thing to bear in mind in here is that although we're choosing regions where we've got contrast in oxidation state, there are other factors clearly that play into the normalized absorption, and so you should always go in and check these regions with another probe to verify that you're sensitive to what it is you think you're sensitive to. But anyway, we found this to be a very nice and efficient technique to interrogate environmental samples of actinides. Okay, so I've got a couple more slides to show, and then I'll pause for some questions. So on this slide, we're presenting similar data for Site B, which is the burial site for heavily contaminated timbers used to construct the target for the DU munitions testing. The evidence here shows that the uranium speciation is quite different. So on this slide, you can see SEM images and laboratory microfocus XRF imaging of typical uranium particulates. And these clearly have a much larger length scale than those at site A. And they have a platy, irregular appearance rather than this nice spheroidal microstructure. So uranium concentration is strongly correlated with the presence of phosphorus, and this supports identification of a uranyl phosphate phase from XRD analysis, as shown on the next slide. Okay, so this slide shows some multimodal microfocus data from particles from site B. The XRD data shows the presence now of this potassium uranyl phosphate hydrate meta-ancoliite together with some residual U3O7 oxide. So consistent with this, the uranium L3 Zanes data show a uranium-6 oxidation state is dominant in these particles, and the edge shift and post-edge features are similar to UO3 or uranyl oxide. In particular, we observe this post-edge resonance B on the figure, which is characteristic of the presence of uranyl species. The XRF map showed the uranium distribution is no longer spherical and spread over a wide area, particularly this example of a particle in image H. And this is again in agreement with the SEM observations I showed on the previous slide. So, you know, for the oxidation conditions, the pyrophoric oxidation of the DU penetrator is clearly not consistent with the formation of a uranyl hydrate species. And so we believe this is formed as a secondary alteration product from weathering of the primary U3O7 particles. So on this slide, we're again using XRF imaging and diffraction imaging combined with oxidation state mapping to kind of pull all this together. So on the previous slide, I showed you that in site B, we have particles which are characterized by the presence of meta-ancoliite as the major phase and residual U3O7. And so the spatial distribution of these phases now gives us some insight into the formation of meta-ancoliite as a secondary alteration phase. So at the top here, you can see we have regions of uranium alpha emission intensity, which are fairly concentrated, but also more diffuse. And if we cross-correlate this with the normalized diffraction intensity using Bragg reflections of U3O7 and meta-ancoliite, what we find here is that we've kind of caught in the weathering process a core of a U3O7 particle with meta-ancoliite forming as a secondary alteration phase. If we go to the oxidation state mapping, we can interrogate this and find that the internal core of this hot particle is reduced, consistent with the presence of U3O7, oxidation state just a little bit above 4, whereas it's surrounded by this massive meta-ancoliite with an oxidation state close to 6. And again, this is confirmed using stepped Zane scanning in the normal way. So to sum this section up, high spatial resolution data on uranium speciation in complex environmental samples has been able to resolve the difference in site-specific behavior of depleted uranium particulates. The data is sensitive to particle variation of uranium speciation and able to resolve speciation gradients within the samples, particularly with respect to uranium oxidation state. We're able to show that depleted uranium oxide particles corrode under specific geochemical conditions, and that's kind of, I guess, as expected, although we didn't necessarily expect to see the extent of alteration that we observed at site B, which has a very different geochemical local environment imposed by the high concentration of organic matter. And so this does show us that depleted uranium oxide particles are stable to some respects over a period of decades in some wet toxic environments, but under some geochemical conditions will undergo alteration to secondary uranal phases. So I'll pause there and take any questions, and you'll be pleased to know that the second part of the talk is slightly shorter.
Okay, thank you, Neil. That was great. Actually, we have already one question by Matthew Marcus. Matthew, do you want to ask your question yourself, or should I do it?
Okay, I was just speculating that energy resolved fluorescence, ACA HERF-D, ACA PFY, might make the chemical mapping easier because it would sharpen up the zanes.
That's right, and we've not actually managed to do one of those experiments yet in microfocus mode. We did have one planned at SLS using a kind of hybrid Johann and von Hamel spectrometer, but that was sort of put off as a result of the difficulties with the monochromator, and now of course nobody's traveling. But that would be a very interesting experiment to do, and is on the horizon. So thank you for the suggestion.
Yeah, and microfocus makes that kind of spectrometry easier because the source size is small.
I'll bear that in mind when I'm doing it, but that's also my understanding. Yes, thank you.
Yeah, thank you. We have a question by Jerry as well. Jerry, would you like to ask directly?
Sure. Hey, Neil. Great talk. What are some of the other challenges in the field of spent munitions, and are any of the other significant challenges also being addressed by XAS?
Good question. So there's actually quite a significant hazard posed by chemical contamination. So, for example, other parts of the system use some metals which are toxic, so things like cobalt. There's a significant tungsten content also. Some penetrators are actually formed of a tungsten, cobalt, and other alloy. And there's a considerable amount of, obviously, residual chemical contamination from the initial kind of explosive charge. So we once did a kind of bacteria culturing experiment in some soils, some contaminated soils, not actually from this site, and it pretty much killed everything. So those are some of the other issues that need to be tackled. But I'm not aware of any sort of significant spectroscopy or other synchrotron methods work being applied to them. But there might be some nice, for example, carbon K-edge and nitrogen K-edge type of experiments to be done with XAS.
Hi, Neil. Danny Vittetti here. I've got another question, if that's all right.
Please.
So in your mapping procedure, are you basically performing like a linear combination fit on each sort of step for the differences in the two spectra at those given energies to differentiate your U4 to U6 ratio?
So it's not really a linear combination fit, because we're not kind of like using two component data sets to fit a third, for example. Essentially what it's doing is it's trying to approximately measure the normalized absorption, and then from the calibration procedure that sort of translates that into a measure of oxidation states with the sort of caveats I gave.
Yeah. And so with those two energies that you're looking at, I can see how that can differentiate between the U4 and the U6, but how does that then differentiate for those other oxidation states that are present, the sort of...
Right, so I guess it doesn't kind of necessarily, I guess maybe differentiates, perhaps not the quite the right word, but in this example here, I guess you see something which is on this scale indicative of an intermediate oxidation state of U5. And then, so if you bring in your diffraction probe here and you find that's U308, then okay, that's kind of sensible. In fact, actually, it turned out this particle was a ternary oxide of uranium-5, which we really didn't expect to see, and was a surprise. But we wouldn't have found it if we weren't able to kind of use this method to sort of interrogate the data on the fly and draw our attention to regions of interest.
That's fantastic. That makes sense. Yeah.
Okay. Thanks for your question.
Thank you.
We have time for a last question by Matthew. Sure. Do you want to ask it?
Hi, Matt.
Hi. Nice work. Actually, there has been some work on other firing sites for lead and antimony. I know some antimony work from Ackerman and et al. From some firing sites in Central Europe. But my question was, have you looked in the X-ray fluorescence maps at the rubidium or the strontium? Because variations in those elements might also affect the sort of background, and so the lowest energy map. And does that affect your most reduced phase?
Great question. And I'll have to try and cast my mind back to the experiments a few years ago now, but we did come across that potassium K beta uranium L alpha emission overlap.
So something like that, yeah.
Yeah. And so I think what we ended up doing was basically doing a fit to the composite emission line to extract the L alpha emission as robustly as we could by subtracting out the potassium K beta or whatever it is. And then I think what we also did was kind of push the energy a little bit up to look at the uranium L beta line as well, which is kind of a little bit isolated. And then we used that to sort of cross-check that our interpretation was sound, is my recollection.
Okay, great. That sounds good. Thanks.
Okay, thanks for your question. Okay, so I've got relatively few slides left. You'll be pleased to hear. So on the second part of the talk, I'm going to focus on using these multimodal microfocus techniques to probe the improved performance of remediation technology for DU contamination at firing range sites. So chemical washing of soils has been postulated as a suitable cleanup technology for DU particulates. And we investigated this with the analysis of reactive particles to probe the mechanism of DU particulate dissolution and provide information for improving the process. So this slide shows the results of batch soil washing and extraction experiments using dilute citric acid, dilute sulfuric acid, and dilute ammonium hydrogen carbonate. So what we did was to take 1 gram aliquots of the soil, and these were extracted at 1 week at room temperature. The lead shape was chemically analyzed by ICP-OES for uranium, and the particles were counted before and after each step by autoradiography. So using this simple approach, we were able to extract up to 50% of the depleted uranium inventory from the soils at both sites using ammonium bicarbonate extraction. And what's interesting is that despite the big differences in uranium behavior and speciation, the extraction is quite similar. And this is pretty much due to the fact that the ammonium bicarbonate is just quite aggressive in its extraction chemistry. So to improve the bicarbonate extraction, we took a look at the partially leached particles to get some insight into the dissolution mechanism. So SEM here shows 2 distinct particle types with evidence of grain boundary mediated dissolution in oxide particles and the formation of secondary phases, as you see here, with this acicular habit. And this was confirmed by micro X-ray diffraction and micro XANES as the formation of, in this case, uranyl carbonate and uranyl carbonate hydrate species. Ammonium uranyl carbonate and uranyl carbonate hydrate species. So this precipitation of secondary phases reduces the extraction efficiency, and that may be more important for highly contaminated soils. So this led us on then to develop an alternative extraction methodology to improve the process. And so really the observation of these secondary uranyl carbonate phases from micro-XRD and microzanes and their characterization led us then to develop a soil washing process combining bicarbonate and citric acid extraction in alternating steps, as you see here. So starting with ammonium bicarbonate, then a citric acid wash, and then a final ammonium bicarbonate wash. So the bicarbonate is effective at leaching the primary particles, and then the use of citric acid essentially dissolves the secondary uranyl carbonate phases that are precipitated. And then we get to go again at the residual uranium oxide material with ammonium bicarbonate. And what you can see from the data on this slide is that the use of this technique provides an increase in the extraction efficiency versus single batch extraction with 68 to 87% of the DU contamination removed after 3 washing cycles. So this is something that could be very simply applied, for example, in a sort of heap leaching methodology on site. We also use autoradiography to track the dissolution of individual particles of uranium, and we see clear evidence of particles being attacked through the leaching process. So to conclude this short second part of the talk, we've used multimodal microfocus X-ray techniques to provide critical insight for the design and improvement of DU remediation technology by probing the extraction mechanisms through characterization of the residual materials. So that pretty much brings me to the end of the core part of my talk. So I'm sure you're all applauding in the privacy of your own homes, but I'll pause there and ask if there are any further questions.
Well, thank you, Neil. There's no question yet in the chat, but I have some myself for the first part, actually. You found some U3O7 using XRD. Did you find as well the right valence states for uranium using your methods for U3O7 particles?
Right, yeah, so I think that's shown, yeah, maybe here on this slide is, I'm sure we've actually got data to back this up. I guess it's like one of these spectra here, but you can see it quite clearly on this slide that you probe an oxidation state of essentially 4.6, which is a little in excess of 4 and consistent with what you expect for U3O7.